Hello, and welcome to Homework 2, Part 2 here. And so this time around, we have a short and straightforward question this time around. And so let's get started. We have, so we're told to derive an expression relating the height of a ball in a rotameter to the volumetric flow rate. So to begin with, let's just sort of draw the scenario here. So I will draw a taper, but I will not consider it just yet. So D naught, we have position 3, position 1, and this difference, this area between the tube and the ball as position 2. And so let's consider it as just a straight tube for now. And so let's say that we're pushing air in, some fluid, right? And well, eventually this ball will reach some steady state, right? And it'll just stop. And from there, well, you use the rotameter, right? And you look at the height or whatever, and it correlates to some flow rate value. And so when it stops, right, its acceleration is 0, and therefore its net force is 0. And so we can sort of calculate the force balance on it and gets somewhere from there. So what are the forces that are acting on this ball? The easiest, I guess you could say, is the weight of the ball, obviously, right? It's free fall inside this tube. And so weight of the ball, it's going to be the mass times the acceleration due to gravity. And so how do we find the mass of the ball? Given only, let's say, the density and the diameter. Well, it's going to be the density times the volume, right? And so we have, hopefully this is still in view of my phone cam. So we have the density of the ball times the volume of the ball, which is going to be pi d naught cubed over 6, right? Because it's going to be 4/3 pi r cubed. D naught is d naught over 2, so 2 cubed will be in the bottom, so that's 8, 1/2, 2 times 3 is 6. All right, and then, so that's the mass, this term's the mass, and then times the acceleration due to gravity. And so in these rotometers, we're gonna have some fluid flowing through, right? So in this case, it could be air. And so there's also gonna be a buoyant force. All right, so this, okay, before I get too ahead of myself here, this weight to the weight of the ball is gonna be going downward, so negative. And then the buoyant force is gonna be acting upwards, so I'll put plus for now. It's the weight of the fluid displaced, right? So weight again, so it's gonna be mass times the acceleration due to gravity. And so the volume displaced is going to be the volume of the ball, but this time the density, right, weight of the fluid, so rho, density of the fluid, times the volume again, and the acceleration due to gravity. So what other forces are happening? It can't just be those two, right? We have the pressure forces at 1 and 3. All right, so pressure force, well, pressure is equal to the pressure force divided by area. So the pressure force is pressure times area. So pressure force at 1 is going to be going upwards. So we have P1 times the area at 1, which is pi d naught squared over 4, right? And then we have the pressure force at 3, which is going to be downwards, right? So minus P3 pi d naught squared over 4. That's all going to be equal to 0, because we said earlier that the net force was indeed 0, because the ball's not moving. And so let me just confirm that this term is correct, right? Area pi r squared, d naught over 2. All right, just making a mental note. So let's do some factoring. Make this look better. So we have rho density of the fluid minus density of the ball. And in front of that will be pi d naught cube g, or 6, plus pi d naught squared over 4. And that's going to be pressure 1 minus pressure 3 is equal to 0. I'll move this around. I'll move this across, so the sign will swap, and I'll move that across too. So we'll have P1 minus P3 is going to be equal to. So this. Okay, let's deal with this factor term out first. So if we subtract this over, it's going to be times 4, so 4 over 6. So we'll have 2/3 divide by d naught squared, so we'll have a d naught. Pi's will cancel. G. And the sign swapped, remember, because we brought it over. So this is now our equation for our force balance. And so from here, we're given some of the stuff, right? We know some of these things, the pressure at 1. We can find out, but then we'll realize something. Well, how do we find the pressure at 3, right? What is even the pressure at 3? So when we look at this ball in a rotameter, right? This ball is small, maybe even tiny, almost, within that tube. And so the distance from point 2, which is at the center, whatever the center of the ball is, to point 3, just outside the ball, top of the ball, I'll say. That's just a distance of 1 radius. And like I said earlier, the ball is already really small. And so we can consider that, or approximate it even, as a sudden expansion, right? There isn't enough length, gradual increase between areas 2 and 3, that is, because we're going from, well, this tiny area at 2, which is the difference between the tube and the ball, to the entire area of the tube in 1 radial distance, right? And so that isn't gradual enough to invoke pressure recovery. And so we can sort of approximate this as a sudden expansion, and thus say then that pressure 3 is equal to pressure 2. And so if we do that, that just simplifies our equation to this. D naught times G, not dog. Okay, and then, all right. And so this is our force balance. Well, we have neither height or volumetric flow rate involved. So what's even going on? Well, this is, well, flow rate, right? And we can relate this to Bernoulli's equation. And so what is Bernoulli's equation? Just to run it through again. Well, it's going to be the pressure difference between 2 points divided by the velocity, the density of the fluid, plus the kinetic energy difference, plus the potential energy difference, is equal to, there's no non-flow work here, so frictional heating. This F. And so we're going to make some approximations here. Like how I said that because the radial distance relative to like the tube and the ball, right, the ball's small, but since we approximated that as being tiny enough to approximate a sudden expansion, this potential energy difference is basically 0, right? So we'll say this is 0. Frictional heating, there might be a super tiny amount between, point 1 and 2, but that distance is so small we can basically approximate it as 0 too. So this is also 0. Volumetric flow rate between points 1 and 2 will be equal, right? And so we can say that V1 times A1 is going to be V2 is equal to velocity at 2 times the area at 2. Solve it for V1. And we can get it in terms of just the second velocity. Second velocity. The velocity at point 2. So simplifying this, we get the pressure difference V2 squared minus V1 squared over 2 is equal to 0. Plug that in. We get P2 minus P1 over rho F. I'll bring this 1/2 out. V2 squared, A2 squared, A1 squared. All right. We can bring a V2 out. So times 1 minus A2 squared, A1 squared is equal to 0. All right. So, the area, so we can make another approximation here. I was just making sure I did this right. Anyway, so the area 2 is going to be this difference between the tube and the ball, right? And that our area difference is going to be so tiny because the ball is already touching the walls of the tube. So this is already almost 0. And if we're squaring that, well, it's going to be for sure 0 at that point, right? So this can be approximated as 0. So we're just left with the one term. So this is just itself. So ultimately, our expression becomes this. And so now we can solve for the velocity at 2. So we'll get V2 is going to be equal to, bring this over, so the signs swap. Rho F. Times 2 square root. And, well, as you can see, well, P1 minus P2 and P1 minus P2. And so that's how these two relate in the end here. And so we can plug that in and we'll get 4/3 D naught G over rho F times the difference between the densities of the ball and fluid. And so we have our equation for the velocity at 2. So we can move on to flow rate, but then you'll realize that, well, we don't have height incorporated at all. So we don't ultimately have our final expression that we need here for part 2. And that's partly because of how I was considering the scenario at first, right? I said that even though I was drawing this taper, which is found in real rotometers, right? I was going to consider it as a straight tube. And so the velocity that we ultimately found was the one for the steady state of the ball, which makes sense because I was saying that the ball wasn't moving. But that's just for a straight tube, and thus that steady state will always be that steady state, if you get what I'm saying. No matter what, only one flow rate will put this ball at steady state in a straight tube. And so that won't help us, right? That isn't even a... Why even call it a rotometer? Why give this useless instrument a name? And so, well, an actual rotometer will have multiple steady states, well, varying volumetric flow rates with varying heights, right? And it will, with a certain flow rate, it'll stop at a certain height. And well, how does it do that? Well, it does that by having a taper within this tube. And well, a taper is this how I drew it here, is this expanding tube going either up or down, right? A taper could be up or down, but in this case, it's going to be going upward for this case. And so, what is this taper relationship? And so, since it's expanding horizontally, right, the diameter is going to be the one that's going to be related to height ultimately. So how does diameter relate with height? Well, just looking at my simple drawing here, hopefully it's on the phone cam. Well, it's going to be just this linear relationship, right? The simplest assumption that we can make that will work. And so considering that, we can say that, well, the diameter is simply just whatever initial diameter at the bottom height plus some slope times the h, right? This is the simplest linear relationship that we can think of that would work for a taper. And so considering that, if we solve for the flow rate here, V2, A2, since the flow rates are equal, and we solve for the velocity at 2, right, we'll just use that. We can say, well, the area 2 is going to be the difference between the area difference between the tube and the ball. So pi d squared over 2, that's the tube, minus pi d naught squared over 2, that's, oh, not over 2, that's over 4. That's going to be the ball, right? And then we can plug that into d squared here. So V2 times, I'll FOIL it in my head here and hopefully not make any mistakes. So d naught squared plus 2 times d naught mh plus m squared h squared. I'll actually pull out the pi over 4 now, minus d naught squared. These two cancel, and ultimately we're left with I'll write q is equal to that. So q is equal to pi v2 4 times 2 d naught mh plus m squared h squared. All right. And so we're finally getting somewhere here with this. We now have, well, flow rate and height being related to each other, but we can actually simplify this expression even further. So actual rotameters, all right, so this picture of mine is probably like super zoomed in, maybe, all right. The ball probably would be a lot bigger, but the taper, just considering the taper, it's probably super zoomed in. In reality, that taper, I guess, slope, if we're relating it to the linear relationship here, that slope is usually a really small number. All right, the taper is very gradual. And because of that, it's near 0, right? And since we're squaring a number that's already super small, it's going to be basically 0 at that point. So 0 times h squared, this term basically gets canceled out, turns into 0. So this becomes pi v2 over 4 times 2 d naught mh. That becomes 1/2 pi d naught mh over 2 times v2. Plug in v2. I'll put h over here since that is the independent variable. Yeah, or, well, whatever, dependent, I guess, technically, if we're putting in a certain flow rate. D naught m 2 yeah, all right, plug in v2. That was 4/3 d naught g over rho f times the difference of densities, right? Yeah. To the square root times h. And so this is ultimately our equation, our expression. We're done. And so in reality, this term, right, it's a bunch of knowns, right? These are all known. M is given usually by the manufacturer of the rotameter that you buy. So ultimately, it can just become some coefficient of proportionality, some number, right? So this could just become that in your user manual. So that is the expression relating the height of a ball in a rotameter to the volumetric flow rate. Thank you.